Hi, I'm Murphy Griffin.
I'm Madison Taylor.
And welcome to episode 14 of Neophyte Boat Rights. In this episode, we're going to go over everything we had to do to expand and loft the transom for our boat. So,
let's get to it.
So what is the transom? The transom is a panel that comes in a variety of different shapes that you'll find at the aft end of a boat. There are lots of different types of transoms. Plumb transoms, raked transoms, reverse raked transoms, cambered transoms, lots of different types of transoms. And because of their often very curved shape and skewed orientation to the rest of the boat, transoms can be often very tricky to both loft, construct, and install. The transom for the Newfoundland Trap Skiff is a standard raked transom. This means that instead of the transom being at 90 degrees to the waterline, it's actually pitched back at a particular angle aftward. In this episode, we're going to cover everything we had to do to loft, construct, and install the transom. Okay, so we're actually only going over the theory and lofting of the transom. We'll be covering the construction and installation in episode 15. So the plans for the Newfoundland Trap Skiff come with a lot of information about the transom. We're provided 3 different views of the transom. One is the view of the transom in the body plan view. One is the view of the transom in the half-breadth view. And finally, what you see in the profile view is actually the expanded transom. In addition to the 3 different views of the transom that are provided in the lines drawing, we're also provided with a number of offsets that we'll need to loft the transom. But unfortunately, just having the offsets isn't enough. We're going to have to do quite a bit more work in order to get the transom lofted so that we can actually construct it. So how does this all work? Okay, so here's our boat in profile. And in blue on the left-hand side, you can see the transom as seen from the edge on. So first, let's see how the various views of the transom that we have in the plans are generated. So imagine you're looking straight back at the transom so that your line of sight is parallel with the water line. Then the view of the transom that you're going to have from this perspective is actually going to be squashed. And this is how we see the transom in the body plan. So while the general shape is correct, the image that we see from this perspective is slightly smaller than it needs to be. So now let's change our perspective so that we're seeing the transom from underneath. Here our line of sight is parallel with the station lines. From this perspective again, the view of the transom that we have is slightly squashed. And in fact, it's even more squashed than the one that we had in the body plan. This is the view of the transom in the half-breadth view. Again, the general shape is correct, but our view of it is skewed. Now, one last time, let's change our perspective once again, but this time our line of sight will be perpendicular to the actual face of the transom. The image of the transom from this perspective is not skewed, and this is the true or expanded view of the transom. This is actually what the transom's supposed to look like. So our objective when lofting the transom is to use the information that we have in the body plan and half-breadth perspective to somehow generate the expanded view of the transom. This process is called expanding the transom. This following animation gives you a sense of how the rake angle of the transom is related to the skewed perspective of the transom. So on the left-hand side, you can see that we've fixed our perspective and we're letting the rake angle of the transom change continuously. As it changes, you can see on the right-hand side that the perspective of the transom is getting steadily more squashed. You can also see that once the line of sight is perpendicular to the face of the transom, that the shape of the transom is at its largest. This should shed some light on why it's called transom expansion. So let's take a closer look at what it is exactly we're expanding when we're expanding the transom. So we're back looking at the transom in the profile view, and one thing you'll notice is that because the transom is raked, the horizontal grid lines themselves are not perpendicular to the face of the transom. Since we're trying to figure out what the transom would look like from a perpendicular perspective, we need horizontal grid lines that are perpendicular to its face. We start with the uppermost horizontal grid line and identify where that grid line intersects the outboard face of the transom, which is shown by a red dot. Then starting from this point, we project a line outward that is perpendicular to the transom's face. We then repeat this process for the remaining grid lines. We now have a new set of grid lines that are perpendicular to the transom. So something interesting happens when we make these new lines. If we compare the distance between the original horizontal grid lines to the distance between the new lines that we just generated, we'll discover that the new lines are farther apart. The amount that these two distances differ is directly related to the rake angle. The shallower the angle, the greater the difference in the distances. So of course, if you wanted to, you could use some trigonometry to figure out exactly what the difference is between these separation distances. But luckily, there's no need to do any of this mathematics or to know exactly what the difference is. The main thing is that we know that the distance between the new horizontal grid lines is definitely greater than the distance between the original horizontal grid lines. So using this insight, we can see exactly what's going on when we're expanding the transom. So if we return to the three views of the transom that we have in our plans, the body plan, half breadth, and the expanded view, and if for each of these three views we add a center line and two consecutive half breadths that are provided in the table of offsets, we can make a couple of observations. So if we select a given half breadth and compare that half breadth in the three different views, we'll notice that these half breadths are all identical. They haven't changed at all, they haven't been skewed. However, if we compare the distance between these two consecutive half breadths in any one of the three views, we'll notice that they're all three different. The distance being at its smallest in the half breadth view and at its greatest in the expanded view. The implication of these two observations is that the skewing that is caused by the rake of the transom takes place entirely in the vertical dimension. So to expand the transom, all we essentially need to do is draw up a new grid work. The vertical lines in our grid work will have the same spacing as the buttock grid lines in our original lofting, but the horizontal grid lines will be expanded according to the projection process that we just talked about. So transom expansion, at least for a simple raked transom, boils down to expanding the separation distance between the horizontal grid lines. But unfortunately, it does get a little bit more complicated. Now, because the planking will be hitting the transom's edge at an angle, we will need to bevel the edge of the transom. So what this amounts to is that we're going to have to loft two transoms, the inboard face of the transom and the outboard face of the transom. So let's see how to loft the transom. So we started by lofting the transom both in the half-breadth view and the body plan view. Now recall that the perspective of the transom in the half-breadth and body plan is skewed, and so it's not particularly useful or needed to loft the transom in these views, but we did it anyways. With those two views lofted, it was time to move on to the expanded view of the transom. Now theoretically, you can loft the expanded view of the transom anywhere you want, but it's conventional and convenient to do it off of the back of the transom in the profile view. So we start by generating the grid work that we'll need to expand the transom. The horizontal lines are generated in the way that we've already described. Remember that the reference point for each of these horizontal projections is where the original horizontal grid lines intersect the outboard face of the transom. Then, using the outboard surface of the transom as our new center line, we draw in the vertical grid lines, all of which are spaced the same distance apart as the buttock grid lines are in the body plan view. Now, lofting the outboard face of the transom is fairly straightforward. We plot all the given half breadths using the new grid work that we just generated. Now, using the lines that we've already lofted, we can refine the shape of the transom even further. If we identify where our first buttock line intersects the outboard face of the transom, and then project that over to the very same buttock line that's in the grid work that we just generated, then we will get a new point that should be on the outboard face of our transom. We can then repeat this process for the other two buttock lines as well as the shear line to get additional information about the outboard face of our transom. The only thing left to do is to add in the points for the top of the transom. Now, the top of our transom is cambered, and there are a lot of different ways to figure out what these points should be. But the top of the transom isn't actually important to the planking process, and so you can really use any shape that you like. And so with all those points plotted, we can loft the outboard face of the transom. Now it's time to turn to lofting the inboard face of the transom. This starts just as it did with the outboard. We need to draw in a special grid work to do our expansion. Only this time the horizontal grid lines have as their reference point where the original horizontal grid lines intersect the inboard face of the transom. We then add the vertical grid lines, which are in the exact same position as they were for the outboard face. The only thing to remember here is that still we're using the outboard face of our transom in the profile view as our effective center line for our expansion. We start by doing the buttock line projections just as we did with the outboard face. We find where the buttock lines intersect the inboard face of the transom as drawn in the profile view, and then project those intersections over to their corresponding grid lines. This will immediately give us 3 points that lie on the inboard face of our transom. But we need more points to complete the lofting of the inboard face. So we're going to use the half-breadth lofting to help us generate new half-breadths for the inboard face of the transom. So to do this, we're going to zoom back in and clear most everything away except a single waterline in the half-breadth lofting and the corresponding horizontal grid line in the transom lofting. So to find a half-breadth for the inboard face of our transom lofting, we're going to start by identifying where the horizontal grid line intersects the inboard face of the transom. We'll then project down from that intersection point to the corresponding waterline in the half-breadth lofting. We can simply then measure the vertical distance from the baseline up to where that projection intersected the curved waterline. This vertical distance will correspond to a half-breadth for the inboard face of our transom. We then simply copy this distance using a pair of dividers or a compass and carry it over to the horizontal grid line in the transom lofting, remembering to measure out from the outboard face of the transom, which is serving as our de facto center line. So doing all this, we've generated one of the half-breadths for the inboard face of the transom. We then carry on this process for the remaining water lines, generating a new set of half-breadths for the inboard face of the transom. We then add back in the buttock projections that we did at the very beginning. Then add in the top points for the cambered top of the transom, which are actually uniformly offset from the originals for the outboard face because the top is slightly beveled. And so with all of these points, we can finally loft the inboard face of the transom. Here's the outboard and inboard loftings for the transom superimposed. You can see that they're slightly vertically offset from one another due to the rake of the transom, and that the inboard is wider than the outboard face because of the beveled edge of the transom. So this is the procedure that we followed to loft the transom for the Newfoundland Trap Skiff. So with the lofting in hand, we could make a template for the transom following the procedure that we've laid out before. Tracing up all the important details onto a piece of drafting film, including the inboard and outboard faces of the transom, the center line, and some grid lines for alignment. And then cut this shape out of the drafting film. Then using spray adhesive, adhere it to a piece of 1/4 inch plywood that we'll use for the pattern stock. And then cut it out with a jigsaw. So after tuning up the shape of the transom template with some sanders, we are ready to start building the transom. So that's episode 14. We really hope you enjoyed it. Stay tuned next time when we'll be going over the construction and installation of the transom onto our boat.
If y'all are enjoying the series, don't forget to like and subscribe below, and consider becoming a patron on our Patreon page. In order to keep the project going, we could really use your support, and any amount really helps.
And so on that note, we have 2 new patrons. Much thanks to
Rick Lapp
and Ed Barker. Thanks.
Bye.
Bye.